My name is Flash Isaac, and I'm a teacher from the future. So I'm taking a look at nuclear energy, binding energy and mass defect, then half-life shall be discussed. Look at something. We've agreed that radioactivity is a nuclear reaction and it is different from chemical reaction. In chemical reactions, electrons are the star comrade, losing or gaining of electron. But when it comes to nuclear reaction, we don't do electron. We deal with nucleus itself. And in the nucleus, we have proton and neutron. Look at something. A heavy nucleus can decide to disintegrate, to split, to form lighter nucleus or lighter atoms. In this case, we said that nuclear fission has taken place where a heavy nucleus splits to form lighter ones. This can happen spontaneously. Spontaneously means without being bombarded, a heavy nucleus can split to form lighter ones. But we can bombard heavy nucleus to form lighter nucleus. That takes us to nuclear energy. Nuclear energy is the energy produced from nuclear fission and nuclear fusion, especially when the energy is used to generate electricity. There are two uranium isotopes. You have uranium-238 and uranium-235, both with atomic number of 92. If you bombard uranium with fast-moving neutrons or with neutrons, you will get barium and krypton, and a lot of neutron will be released plus energy. In this case, uranium-235 has given us barium 141, krypton 92, and a lot of neutrons plus energy given off. What has happened? Uranium is heavier than barium and is heavier than krypton. Therefore, fission has taken place. Heavy form two lighter ones. Then we have nuclear fusion. Nuclear fusion. Nuclear fusion. Fusion or fuse is when lighter nucleus or lighter elements combine, they collabo to form a heavier one. In that case, we said fusion has taken place. Look at this. This is deuterium. Hydrogen with atomic mass of 2 is deuterium. It is a hydrogen isotope. Reacts with tritium, hydrogen of mass 3. Both have atomic number of 1. In this case, they form a helium nucleus. Atomic number mass 4 and atomic number 2. Plus release of neutrons and energy. If you look at this, helium is heavier than this and it is heavier than this. We say fusion has taken place. The energy from the sun or energy in the sun is produced as a result of nuclear fusion. Meanwhile, the energy gets to us by radiation. Don't confuse these two things. Energy from the sun is produced as a result of nuclear fusion, but it gets to us via radiation. There is no material medium. Look at something interesting. If uranium is bombarded with neutrons to give us barium and krypton plus release of neutrons, these neutrons, as there are so many, they will keep bombarding other materials for a continuous fission. Let's say this guy is bombarded with neutrons to produce 2 nucleus plus neutron and energy. And this neutron bombards another material again. Then fusion takes place. A process where one fission leads to another, one fission leads to another is referred to as chain reaction. chain reaction. We try to control nuclear fission, or we try to control the chain reaction using moderators. Moderators are used to control the chain reaction or to control nuclear fission. A good example of moderators are graphites and heavy water. They are used to slow down neutrons in nuclear reactors, because the faster the neutrons move and they continue to bombard, you will see a lot of fission. One fission happens, another happens, another happens. To reduce the rate of fission, we use graphite and deuterium oxide, which is referred to as heavy water, to slow down the neutrons from bombarding the radioactive material. But if you want to stop the neutrons completely, you use carbon and boron materials. These are moderators in nuclear reaction. It is because one nuclear fission leads to another. We therefore need to moderate the neutrons or stop them. And that happens in nuclear reactor or atomic pile. That is the explanation for that. Now, applications of nuclear fission and fusion. Nuclear fission finds application in atomic bomb. It is used to make atomic bomb or fission bond, and it has a very wide application in nuclear reactor, like I just explained. Then nuclear fusion, FU, is used to make hydrogen bomb, or you call it fusion bomb. And energy from the sun is as a result of nuclear fusion. I hope I've been able to explain something. Now, binding energy and mass defect. This is the idea of binding energy and mass defect. Get it now and get it now. When studying, you will be told that mass is equals proton plus neutron. That is atomic mass. At a time, we find out that you look at some atoms or some elements. Let's say the proton is 2.1 and the neutron, just example, is 2.2. Ideally, the mass is supposed to be 2.1 plus 2.2. If I am correct, 4.3. In reality, you will realize that this thing is not up to 4.3. It is around 4.25. What has happened? Mass defect. That is mass defect for you. You go to the bank, you deposit 500 naira in a new account. The next day, you deposit 500 naira. Thursday, you deposit 500 naira. 500 naira plus 500 naira plus 500 naira is supposed to be 1,500 naira. But surprising for you, you check your account balance, you are seeing 1,450 naira or 1,490 naira. This doesn't add up because 500 plus 500 plus 500 naira is supposed to give you 1,500 naira, which means there is a loss. Now, what is the reason for mass defect? About this time, try to explain to us that E is equals mc squared. The binding energy is equals the mass defect times the square of the speed of light, which means the reason for this mass defect is binding energy. What is binding energy? Matter, or the mass in the case, is converted to energy, and that energy is what is used to hold the atom together. Let's put it this way. If this is proton plus neutron, this is the nucleus, or this is the atom. If the mass is supposed to be 4.3 and it is now 4.25, the mass that is lost, that mass is converted to energy, and it is this energy that is used to bind the atoms together. So binding energy is the reason for mass defect. And the equation combining energy and mass or relating energy and mass is E equals mc squared. This is the speed of light. Einstein also made us understand that we can convert matter to energy, because matter is anything that has mass and occupies space. Energy is antimatter. Energy doesn't have mass, it doesn't occupy space. It can be classified as wave. It is not a particle. So, to convert energy to matter or matter to energy, you simply say that the energy is the mass defect times the square of the speed of light. And speed of light is 3 times 10 to the power of 8 meters per second. That is the velocity of light. Look at a popular question. We have boron. The atomic mass of boron is 10.8 Ju, unified atomic mass unit. But mass is proton plus neutron. The mass of proton is 1.0073 U. And the mass of electron is 1.0087 Ju in terms of unified atomic mass unit. Having this, what is boron? Hydrogen, helium, lithium, beryllium, boron. Hydrogen, helium, lithium, beryllium, and boron. Boron has atomic number of 5. And the atomic number 5 is the number of proton. The atomic number of any element is the number of proton in the nucleus of that element, which means boron has 5 proton. And boron has 6 neutron. Neutron is equals 6. That is the number of neutrons in boron, because the mass minus the number of protons will give you number of neutrons. If boron has 5 protons and 6 neutrons, the mass of proton is 1.0073 unified atomic mass unit, and the mass of neutron is 1.0087 unified atomic mass unit. And we are told that atomic mass is proton plus neutron. Since the mass of proton is this and the mass of neutron is this, and boron has 5 proton and 6 neutron, it therefore means that the mass of boron is supposed to be 5 proton, 5, 1.0073 plus neutron, 6 neutrons. 6 times the mass of neutron, 1.10087. If you solve this, you will get 11.0887 Ju. This is the mass of boron you are supposed to get. But in reality, the mass of boron is actually 10.8 units, which is less than the number of proton plus the number of neutrons. And 10.8 units, 81 units, and 11.00887 Ju, if you subtract, you will get 0.278 Ju. This is the mass defect, the defect in mass. So this has been lost, converted to energy to hold the nucleus. So these are the typical questions you will get under mass defect and binding energy. So you're given, we know proton, we know neutron, and the number of proton and neutrons. When you multiply and add, it is usually bigger than the mass you are given. So you subtract what you got from the mass you are given to get the mass defect. And like I said, according to Albert Einstein, E is equals change in mc squared. Binding energy is change in mass defect times the speed of light. Change in m is the mass defect. This is the mass defect. So mass defect times the speed of light, you will get the binding energy. And sometimes you'll be asked to look for binding energy per nucleon. Binding energy per nucleon is simply the binding energy that you have divided by the number of nucleons. Nucleons are protons and neutrons. So in the case of boron, the number of nucleons equals 5 plus 6. 5 protons, 6 neutrons. 5 plus 6 is 11. So we have 11 nucleons. Binding energy divided by the 11 nucleons. That is what you get And to get bending energy, you multiply the mass defect times the square of the speed of light. Up next is half-life. Natural radioactivity is the spontaneous disintegration of the nucleus of a radioactive material or unstable material to give us radiation. While artificially, we can bombard stable nucleus to give us radiations. If this is a radioactive material, it starts decaying, radiation have been emitted. It decays to the extent it gets to here. So the time taken for the radioactive material to decay to half of its original mass, because this is the original mass, it has decayed to this point. It is now half of the original mass. That is referred to as half-life. It is T1/2. And these are formulas for half-life, which we shall be applying them very, very soon. Under half-life, you should be asked to look for the fraction that is left. What is left after so decay? The fraction left is 1/2 or half raised to the power of T0 over T half, which is 1/2 raised to the power of n. N is the number of half-life. T0 is the time you are given, and T half is the half-life. Which means, if I say that you should define the fraction given when half-life is 2 years and time after 5 months, what fraction will be left? A radioactive material with half-life of 2 years, and after decaying for like 6 months or 1 year, what fraction will be left? You simply substitute the time given here and the half-life, you have the fraction that is left. And the time given divided by half-life is the same thing as n, where n is the number of half-lives. Which means, if I say find number of half-lives, you can simply say the time given over the half-life. That is the number of half-life the material we have. If this is fraction that is left, fraction that is lost plus fraction that is left is equals 1. Which means, if you are given a question to find fraction that is lost, you simply use this formula to calculate fraction that is left. 1 minus fraction that is left is the fraction that is lost. It's just like probability. Probability of event happening is equals 1. It doesn't exceed 1. Which means the fraction that is left can never get to 1. You can subtract 1 from it. Nf over Ni is equals 1/2 raised to the power of n. If you are given a radioactive material, you are given the final mass after the decay or disintegration, and you are given the initial mass or number of particles before the disintegration. Number of particles after disintegration, or the mass or the material after disintegration over before disintegration is equals 1/2 raised to the power of n, where n is number of half-lives, which is also the same thing as T0 over T half, time given over half-life. So this you are seeing here can be rewritten as inverting Ni over Nf is equals 2/1 raised to the power of n. This is equals fraction that is left. And decay constant is 0.693 divided by half-life. If you are given decay constant and asked to look for half-life, you simply say 0.693 divided by decay constant. These are the top formulas, all the formulas you may need to answer radioactivity question. Which of these chemical species has no neutron in the nucleus of its atom? Has no neutron in the nucleus of its atom. Remember that an atom is made up of nucleus, and in the nucleus we have proton and neutron. The electron revolves around the nucleus. Out of beryllium ion, hydrogen atom H, lithium ion Li plus. Don't worry, we'll look at the charge later. lithium ion and helium atom. Helium atom. Which of them has no neutron? Now look at beryllium. We have hydrogen, helium, lithium. So lithium will form one ion because it has one electron in the atom's shell. Once it gives that out, it becomes positively charged. So hydrogen, helium, lithium, beryllium. Beryllium has two electrons in the atom's shell. So if beryllium is giving them out, beryllium becomes 2 plus. Now, the number of proton is the atomic number. Equals proton. Then proton plus neutron is equals mass. Therefore, neutron will be mass minus proton. Now, hydrogen atom is atomic number of 1 and it has mass number of 1. So, the number of neutron is mass minus proton. If the mass of hydrogen is 1 and the number of proton, atomic number, is 1, neutron is equals 0. So hydrogen atom does not have neutron. And hydrogen ion does not have electron. Hydrogen ion is simply only proton because hydrogen has 1 proton and 1 electron. By the time hydrogen loses the only electron it has, it no longer has electrons. It has only proton. So when we say acid is a substance which when dissociates or dissolves in water produces hydrogen ion as the only positive ion, we are trying to say that acids are proton donor because hydrogen ions are proton. Then helium atom obviously has neutron since the atomic number is not even 1, it's more than 1. Helium has a mass number of 4, atomic number of 2. So 4 minus 2, that is 2. Neutron is equals mass 4 minus proton 2, that is equals 2. Ladies and gentlemen, lithium ion also has proton. It is hydrogen ion that doesn't have proton. Which of the following involves a beta particle emission? Which of the following involves a beta particle emission? Ladies and gentlemen, you must not learn to forget. The fact that this episode is treating questions under radioactivity does not mean you should forget everything we've done so far under radioactivity. The intro, the particles, the radioisotopes, in fact, mass defect, half-life, binding energy, nuclear energy. You must not forget any of them. And I told you that beta particles are fast-moving electrons. When an atom or a nucleus emits beta particle, the atomic mass remains the same. The atomic number increases by 1. So, out of A, B, C, and D, the one whose atomic mass remains the same and atomic number increased by 1 actually emits a beta particle. Option A, no. Option A emitted alpha particles. Alpha particle is helium nucleus. When alpha particle is emitted, the mass will reduce by 4 and the atomic number will reduce by 2 as seen in option A. Option B, the atomic mass remains the same, atomic number increased by 1. That is beta particles for you. For option C, the atomic mass reduced by 4, atomic number remains the same. No. Option D, no. So option B is this phenomenon where beta particle is being emitted. Which of the following denotes alpha particle? Option B is alpha particle. E is supposed to be 4, that's an error. So an alpha particle is a helium nucleus. Option A simply denotes neutron. Option C denotes beta particles. What is emitted during the disintegration of barium nucleus as shown by the equation below? The equation below gave us barium. mass number 138, atomic number 56. Then in the product side, the atomic number has reduced by 2 and the mass has reduced by 4, which means alpha particle has been emitted. When an alpha particle is emitted, mass drops by 4, atomic number drops by 2, because alpha particle is a helium nucleus. An atom, atomic number 92, mass number 238. This should be uranium. Decays by alpha particle emission to give an atom Y. The atomic number and mass number of Y are dash. If S 2, 3, 8 and 92 decays by alpha particle emission, which means it has emitted alpha particle 4 He. So emitting alpha particle, it means that 4 has been removed from this mass. What is produced? Y. We have 4 minus 238. That is 2, 3, 4. Then, since alpha particle is emitted, atomic number will drop by 2, which means 92 minus 2. What is here? We have 90. Is that thorium? Probably. So, looking at the options, the atomic number and mass number of Y are, atomic number is 90 and mass number is 234. Option B is looking very, very correct. And proton is being released. For proton, the atomic number is 1. Obviously, no neutron. The mass is 1. So, what is A and what is B? In a nuclear reaction, this is how to balance equation. Balancing the mass, we know that 14 plus A should be equals 17 plus 1. Obviously. And for the atomic number, 7 plus B should be equals 8 plus 1. 7 plus B is equals 9. Therefore, B is equals 9 minus 7. That is 2. Here, 14 plus A is equals 17 plus 1. 14 plus A is equals 18. A is equals 18 minus 14. That is 4. So, S has atomic mass of 4 and atomic number of 2. Therefore, that is an alpha particle. S is an alpha particle. In the reaction below, S and Y respectively are dash. We are given thorium. Thorium decayed to give us Pa and beta particle. I've forgotten the compound Pa, but it doesn't mean. Look at it. 2, 3, 4 thorium 90 to give you SPA Y plus beta particle. When beta particle is emitted, beta particles are fast moving electrons. So beta particle is this, electrons. Here is minus 1 and here is 0. So let us balance the nuclear equation. Like we did here, for this guy, 2, 3, 4 here equals S plus 0. So S is equals 0 minus 2, 3, 4. That is 2, 3, 4. Which further proves that for a beta decay, atomic mass remains the same. Here, 90 plus 90, this is side, then this is equation. 90 is equals Y plus minus 1. 90 is equals Y plus times minus is minus Y minus 1. Therefore, collecting like terms, 90 plus 1 is equals Y, which means 91 is equals Y, and Y is equals 91. This proves that for beta decay, atomic number will increase by 1. So Pa, S is 234 and Y is 91. Option A is the correct option. The emission of two successive beta particles from the nucleus of P1532. What is this atom? Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus. Although the atom doesn't concern us, phosphorus emitted two successive beta particles from the nucleus. So which means here gave us one beta particle plus another beta particle. What would happen? Since it gives us two beta particles, what is remaining? Let's call it S. When an atom emits a beta particle, the atomic number will increase by 1. When an atom emits two beta particles, the atomic number will therefore increase by what? 2. Which means instead of 15, we have 16, 17 here. And here, instead of 32, 0, 0, 0, 32 remains. So it is 32, 17. Option A is the correct option. Nuclear fission involves the splitting of energy and radiation in two nuclei of dash. A. Unequal masses without any release of energy. B. Nearly equal masses with a release of energy. C. Equal masses with a release of energy. And D. Equal masses with a release of energy and radiation. Now, nuclear fission is a process of generating nuclear energy, as well as we have nuclear fusion. The energy from the sun is produced as a result of fusion, and it reaches us by radiation. Now, fusion itself involves splitting of energy and radiation in two nucleus of nearly equal masses with release of energy. When a nucleus splits, it releases two different atoms of nearly equal masses, not equal. It can never be equal because some have been converted to energy. So nearly equal masses and energy is released. So option B clearly explains nuclear fission. What is the value of S in the nuclear reaction above? Radium gave us RON and alpha particle. Now, obviously, once an alpha particle is released, mass will drop by 4 and atomic number will drop by 2. So the value of S is simply 226 minus 4. That is 222. Option C is the correct option. And which of the following represents positron? We are told that electrons are negatively charged. True or true? True. Ladies and gentlemen, there are cases where you see positive electrons, and these positive electrons are referred to as positrons. So option B represents positrons, while option D represents electrons or beta particles. While I was explaining half-life, I gave all these hot cake formulas. With this, you are settled when it comes to calculating half-life in radioactivity. Look at this question. A radioactive nucleus has a half-life of 20 years. Starting with 100,000 particles, which means the initial particles, Ni, is equals 100,000. How many particles will be left at the end of 40 years? Left is equals question. Time, which is also T naught, is equals 40 years. We are given Ni, we are given T naught, we are given half-life, we are asked to look for the fraction left. Remember, the fraction left is equals 1 over 2 raised to the power of T naught over half-life. We can use that formula. We can as well use this formula to calculate fraction that is left. So Ni over Nf is equals 2 raised to the power of n. We can use this to calculate fraction that is left. Ni is equals 100,000 over Nf. This is equals 2 raised to the power of. Remember, N is T naught over T half. T naught is time given, T half is half life. So this is raised to the power of T naught 40 over half life 20. This is the same thing as 100, 1, 1, 2, 3 over Nf is equals fraction, original fraction over left is equals 2 raised to the power of 2. This will be 40 divided by 20, that is 2 now. 2 raised to the power of 2 is 4. So this is equals 4. Therefore, the fraction left, this final, will give you 100, 1, 2, 3 over 4. This is equals Nf. 100,000 divided by 2, that is 50,000. 50, 1, 2, 3. 4 divided by 2, that is 2. This is equals Nf. 50,000 divided by 2, that is 25,000. So 25,000 is simply the particles that is left. So from this formula, here is the initial particles given. As you can see, starting with 100,000 particles. This is the starting particles. This is will not be particles remaining. This is equals 2 raised to the power of n. N is the time given over half life. This is the same thing as T naught over T half. So that is basically it. For a certain radioactive material with a half-life, T half is equals 50 days. To reduce to 1 over 32 of its original mass, Ni is the original mass, is dash equals question. The time, which means we are looking for given time, it will take for a radioactive material to reduce to 1 over 32 of each original is dash. From here, we are looking for the given time, we have half-life. This formula will always come to our rescue. The initial mass given over the final mass is equals 2 raised to the power of n, where n, okay, let's say 2 raised to the power of n. Now, the initial mass is Ni. The final mass, Nf, or what is remaining, is now 1 over 32 of Ni. That is Ni over 32. So we have Ni to be Ni, and we have Nf to be Ni over 32. Let's resolve this. This is Ni divided by Ni over 32. This is Ni times 32 over Ni, changing division to multiplication. So this cancels this. Everything here is 32. So everything here, 32 is equals 2 raised to the power of n. Now, there are many ways you can answer this. Either you apply indices or you have to use log. But since you can use indices to resolve this, it will be easier for you. It's 32 and this is equals 2 raised to the power of n. Indices says when the bases are the same, you equate the power. So 5 is equals n. Now what is n? N is time given over half-life. So 5 is equals time given, that is what we are looking for, over half-life is 50 days over 50. So time is equals 5 times 50. That should give you 250 days. That is the correct thing. On the other hand, if you choose to go the hard way, you can say that 32 is equals 2 raised to the power of n is T naught over half-life over 50. So if this is what you want, you do that. But that is basically it. With these formulas, you can solve anything under half-life. A radioactive isotope has a decay constant of 10 raised to the power of minus 5 seconds. Decay constant. Constant is equals 10 raised to the power of minus 5 per second. Calculate its average life. Average life is simply the half-life. And from here, decay constant, 10 raised to the power of minus 5 is equals 0.693 over half-life. So decay constant is 0.693 divided by half-life. Half-life, T half, is therefore 0.693 over 10 raised to the power of minus 5. 10 raised to the power of minus 5, that should give you 0.00001. Yes, 0.00001. So 0.693 divided by dash, that will give you 6.93 times 10 raised to the power of 4. Option C should do justice to that. Thanks for watching. Your one and only teacher from the future. I hope you found this class interesting. Feel free to check out the playlist for more amazing videos. And don't fail to install the Flash Learners application right now for notes, videos, and questions to meet all your needs. Subscribe to this channel so you don't miss out any of my sweet videos. See you in the next episode. Don't forget to tell everyone around about the Flash Learners. Bye.